Compositions of Phobos and Deimos, the view from visible to near-infrared spectroscopy.
Great, thank you. Wonderful. All right, thank you so much, and thanks for traveling with me now to Mars, and of course its moons, Phobos and Deimos. Today I'm going to be talking to you about kind of a summary of work that we've done over the last 5 years, looking at some new observations of Phobos and Deimos in the visible to near-infrared portion of the spectrum, and discuss what we've been able to conclude from these data about what the moons are made of. Now, before I go into the data, I just want to give a little bit of context about Phobos and Deimos and talk about why, a little bit, these moons are so interesting. First of all, these moons are a target for scientific exploration. The question of the origin of these moons is one of the big outstanding questions in planetary science. And there's sort of two major schools of hypotheses that are floating around the community today. The first is that Phobos and Deimos could be captured asteroids, either collected from the inner solar system or from the outer solar system. And the second is that these moons may have formed in situ around Mars, either by an impact into a differentiated Martian crust or through co-accretion with Mars. Regardless of which of these origin scenarios is the case, the presence of these moons is particularly interesting because they reflect relics from the earliest portion of our solar system. So by studying these moons, if they're captured asteroids, this is an opportunity to study kind of primitive material from the solar system, and especially if they're from the outer solar system. These would represent some of the most accessible bodies of this kind of formation process and from the outer solar system. And if they formed in situ with Mars, they may represent kind of the earliest, most primitive Martian crust, or may represent kind of a composition of a bulk Mars. So either way, these moons are really interesting from a scientific perspective to tell us about the earliest time in our solar system. Of course, as we discussed yesterday, these moons are also interesting from a human exploration perspective because they could be used as staging bases for an eventual manned mission to Mars. In terms of why we're interested in the composition of Phobos and Deimos, this again has implications both for scientific exploration and for human exploration. In terms of the science, the composition will have a direct correspondence to how these moons formed. So if the moons are indeed captured asteroids, we'll expect them to have a composition that's similar to captured to meteorites or to asteroids, kind of primitive materials, either carbonaceous chondrite-like materials. If the moons form from a differentiated Mars, we'd expect them to have a composition that looks like what we found to be kind of a typical basaltic Martian crust. And if the moons formed by late-stage co-accretion with Mars, they may have a composition that's more similar to a bulk Mars composition, something like an ordinary chondrite. In terms of the human exploration side, we're interested in the composition of these moons because they could potentially provide in situ resources for any manned missions to the moons or to Mars. Our view of their composition in the mid-2000s was kind of two big things were known. We knew that both of the bodies were very dark, and we knew that Phobos had kind of two types of materials on it. We know some of the material on Phobos was this spectrally bluer material. And here's a combination of spacecraft and telescopic data. So Phobos had some spectrally bluer material and some spectrally redder material. In this top figure I'm showing, this is a plot from a Murchie and Erard paper from 1996. And you can see this shows kind of the color of Phobos, and around this feature here, this is Stickney crater. It's a 9-kilometer diameter impact crater that kind of dominates the geology of Phobos. We see that there's a lot of bluer material versus other parts which look a little redder, and I'll cheat a little bit and show you a high-rise image of that same area. Here again is Stickney, and so we can see Phobos has blue stuff and it has red stuff. Deimos looks like Phobos' red stuff. But in terms of looking for diagnostic mineral absorptions, there really hasn't been any defensible detections above the level of instrument noise of any diagnostic absorptions such as olivine or pyroxene. We do know that the slope and the albedo of the moons are similar to what we see in asteroids such as the D-type or the T or the P-type asteroids. In about 2007, the Mars Reconnaissance Orbiter did a couple dedicated observing campaigns of Phobos and Deimos where it used its suite of instruments to observe the moons. Here I'm showing CRISM observations. That's the Compact Reconnaissance Imaging Spectrometer for Mars. CRISM has one observation of Phobos and one observation of Deimos. CRISM images Phobos and Deimos from 0.4 to about 4 micrometers, and it has a very high spectral resolution. This is the sub-Mars hemisphere of both of these moons. They're tidally locked, so you have the same side facing Mars. So this is the side of the moons that face Mars. And this actually represents the first disk-resolved hyperspectral image of Deimos that was ever acquired, and the highest spectral resolution of Phobos that was ever acquired. And for context, here we have images that were taken of the moons from the HiRISE, the high spatial resolution camera. So this doesn't have the spectral information that the CRISM observations has, but it has a high spatial resolution to give us context for these images. The Mars Express, this is the European orbiter, also has been involved in several observing campaigns of Phobos. Because of the orbit of Mars Express, it's actually able to image both the subsurface side of Phobos and the anti-Mars surface of Phobos. So it's imaged a wide range of the surface of Phobos. And again, on top I'm showing these are images that were acquired by Omega. So that's the visible to near infrared spectrometer on that mission. And that has a very similar wavelength range to CRISM from about 0.4 to 5 micrometers, slightly coarser spectral resolution. And again, here are some context images that accompany the Omega data from the HRSC high spatial resolution camera. And you can see they're acquired at a range of spatial resolutions, and importantly, the Omega data set was acquired at a range of different lighting and different viewing geometries. So here's an example of what some of the spectra look like from the CRISM and the Omega observations. So here I'm showing on the bottom of the screen, these are regions where spectra are pulled, and in particular, look at the red box, that's where these spectra are coming from. And here in this black line up top, this is what the Deimos spectrum looks like from the CRISM data. In red is what the Phobos spectrum looks like, and in orange is what the Omega spectrum looks like. First of all, you notice that these spectra look pretty flat. They are getting brighter with wavelengths, so they're all spectrally red. But what you also notice is in terms of raw I over F, these spectra are all very different in terms of their slope and their brightness. And this is because they were acquired under this range of lighting and viewing geometries. What we were able to do using the Omega data that were acquired at all different viewing conditions was to derive the spectrophotometric properties of these moons in order to model how they behaved when viewed in different lightings. So what we did was we derived these properties, and then we applied this model to both the Omega data and the CRISM data in order to solve for a quantity called single scattering albedo, which is independent of lighting and viewing geometry. So when we do that, you can see when we solve for the single scattering albedo of all of these points, we see that in terms of the red unit, the CRISM Deimos and the CRISM Phobos and the Omega Phobos data now all line up really nicely. And they give us consistent results between the two instruments, and they show what we'd seen in previous data sets, that the Phobos red stuff looks a lot like Deimos. And one of the powerful things we could do now that we knew the single scattering albedo of the moon was to use our model to recast what we saw to any arbitrary lighting and viewing geometry. So this allows us to directly compare the slope and the absolute magnitude of these spectra to things that we measure in the laboratory, also under very controlled lighting and viewing conditions. So we did this, and we looked through a whole bunch of spectral libraries. A lot of them were from the Relab instrument, comparing what we see in Phobos and Deimos to materials that we may have measured here on Earth. And we found that the only thing that was dark enough and that had a similar slope to what we see in Phobos and Deimos, the things that most closely matched were CM carbonaceous chondrites. So here, this figure on the left, I'm showing this bluer material, the blue unit spectra from the Stickney ejecta from inside of Stickney, compared to several CM carbonaceous chondrites. Here's a Murchie that's been heated, Miggy, and Tagish Lake, which is actually an unusual carbonaceous chondrite that is thought to be sourced from a D-type parent body. But what we can see is that the Phobos data really nicely match these spectra in the blue unit. The red unit, we don't get as nice as a match in terms of absolute magnitude, but we do see, again, similar slopes and similar absolute magnitudes to these carbonaceous chondrites. Something else we can do in order to test the hypothesis, perhaps these surfaces are really space weathered. Maybe they are initially much brighter basaltic materials that have been really space weathered, which makes them darker and which may remove some of their absorption bands. So we also compared these spectra to features that we see in mature lunar mare and also with Mercury spectra. And again, when we compare them to the same lighting and viewing conditions that we would observe on these surfaces, we see they're not as dark as what we see on Phobos. And you can imagine Deimos down here as well. So with the lunar spectra, they're still brighter. We still see a hint of this mafic absorption here. Again, on Mercury, it's still brighter than what we see on Phobos and Deimos. We also use the CRISM data to search for any spectral features and spectral absorptions in the moon, because this data set has a very well-known calibration and high spectral sensitivity. And these are showing band depth maps where we're trying to search for olivine olivine, high calcium and low calcium pyroxene, or features indicative of overtones for hydration. And you can see that there's not much that shows up here. What we did find was a feature located near 0.65 micrometers. So here's that 0.65 micrometer band depth. We have to do it at 0.6 because there's a boundary in the CRISM detector right here that precludes data. But you can see that there's this sort of feature that shows up on the moon. It has a nice correlation. This is showing the redness and the blueness of the Phobos and the Deimos data. So you see where it's blue on Phobos, we don't see the feature. Where it's red, you do see the feature. This dotted line is a continuum, so you can see the red and the blue, the red stuff kind of dips below the continuum. And in case you really don't believe me, this is a real feature. We went back and we looked at some telescopic data centered over the Phobos red and blue unit. You can see here's the blue data, here's the red data, and it lines up beautifully with what we were able to observe with CRISM. And I'll also say there's a really nice pair of papers that recently came out looking at the Rosetta flyby data over Phobos, and we see that this data was centered over the sub-anti-Mars hemisphere. That's the really red portion of Phobos, and we see that they also saw this feature. So this has been observed in multiple data sets. We also spent some time looking at this portion of the spectrum, and we found a feature at 2.8 micrometers. This is a tricky portion of the spectrum to work with because you have to take into account contributions from both reflected solar radiance and also thermal emission. But here is showing the reflected solar radiance modeled portion of the spectrum only, and you can see that there is this checkmark dip at 2.8 micrometers. Here's our band depth map. The data are noisier. The signal to noise of the instrument is lower here. But you can see there is kind of a correlation between what we see here and what's blue. We see it's a less deep feature, and red it's deeper. What was neat is we see these features all over the solar system. So here's the 0.65 band compared to other dark asteroids. And here's the 2.7 feature, again, compared to other dark asteroids. We see this kind of check mark is very common. And in terms of interpretations, this was a non-trivial interpretation for us. We kind of came up with two hypotheses that sort of explain what we see. The first is that the pair of features is caused by desiccated phyllosilicate. So here's an example of a nontronite that's been heated, and you can see it creates a band in a similar position. We see phyllosilicates a lot. They're a dominant mineral in CM carbonaceous chondrites. And then the second explanation was that they may have been caused by space weathering. So you'd have OH created on the surface in a process similar to what's thought to be happening on the moon. And this 0.65 feature can actually be caused by models of creations of blebs of nanophase iron oxide. So here's a model we made with nanophase iron, and you can see we got the shape to fit what we're seeing in Phobos very nicely. So just to run through the key conclusions, these moons are darker than even the most space-weathered materials. They likely have a carbonaceous chondrite-like composition. The pair of spectral features we've observed are similar to those seen on other low albedos. So if you want to argue that the more moons formed in situ, you have to either discuss how they are made of carbonaceous chondrite type materials, or explain how these dark materials could have been added to the Martian system. So I'll leave it with some thoughts about what's next, and I'll take any questions.
So this is really interesting. The comparison between Phobos and Hector, which is a Jupiter Trojan, is really shocking, and it actually seems to work. Now, at ACM just a few weeks ago, Mike Brown was talking about how when he looks at the Trojans and he looks at the outer main belt asteroid, he looks at the things in the Sibelius and the rest, they're all showing, it almost looks like hydration features beyond about 3 microns or so. And they all look like they may be all the same kind of stuff, including irregular satellites. It looks like we can add Phobos to this list. What do you think of that?
I think that's a very viable hypothesis, but as a dynamicist, now I have to ask you, what do you think of that hypothesis?
Oh, God, I don't know.
Yeah, spectrally, that's what they look like, and the papers from the 90s say these are D-type objects, just like the Trojans, but...
Phobos and Deimos have been torturing us for a long
Yeah.
time. They're going to continue to torture us, I think. So, but it does seem like there's a connection there, so it's interesting.
Okay, moving right along.